This will be a surprisingly weird example with the improper integrals, but also practicing again trig substitution. So we are asked to talk about physics. In electromagnetic theory, the magnetic potential U at a point on the axis of a circular coil is given by the equation U is A times R, which are constants, an integral from A to infinity, A is a constant as well, dx all over R squared plus x squared raised to the 3/2. So all those things, they mean something, and if you're curious, just Google what it means. So we asked to find that U, basically calculate the integral. Well, maybe you need to review what kind of trig substitution we use. So if you have a square root, constant squared minus input squared, we use sine. Input squared minus constant squared, we use secant. And the only one with plus, we use tangent. So that's the one actually we're going to use here because we are working with the plus here. And there is a square root. Do you see it or not? Should I rewrite this for you so that you can see this hidden square root? Every time I see division by 2 in the exponent, then I know, oh, that's actually square root. This is integral AR times AR, integral from A to infinity dx all over a square root R squared plus x squared raised to the 3rd power. And now we definitely should see that we should use tangent for this case because it looks like so. Okay, let's do it. Let's start the fun game with lots of trigonometric functions. Like I like to make joke about it. It already looked bad and now we want to introduce. So let x be r tangent theta. Introduce some trigonometric function to basically make it worse. But it's a joke. It's actually gonna help you because trig identities work out pretty well. So because of this r constant, we need to multiply. This is a in this formula. R was squared, so there's going to be a times tangent, but in this case it's r times tangent. Now then dx is r secant squared theta d theta. Remember that. And also we need to change limits of integration, so we're actually not going to be bothered by limit integration for now. Let's just solve the indefinite integral and then see how it goes at the end. That will be easier this way. Because it's an improper integral, so we need to use limits and stuff. Then integral of dx all over r squared plus x squared, a square root cube, is going to be integral dx is r secant squared theta d theta. Now what's inside of this square root? R squared plus x squared, but x is r tangent theta, so it's going to be r squared tangent squared theta. You could factor out r squared right away if you feel comfortable, but don't forget about the cube. That will be important. Cube is still there. Now, why do we do that? Remember from the previous chapters, we want to factor out this r squared. Why? Because then we will have 1 plus tangent squared, and that's secant squared. Integral r secant squared theta d theta. We're factoring out r squared, so it's going to be r squared 1 plus tangent squared theta, but r squared inside of the square root is just r. Then I have a square root 1 plus tangent squared theta, but also be careful, everything is still cubed, including the r which you kicked out outside of the square root. Be careful about that. So r is still cubed. Okay, not too bad. Now what we're going to do? We are going to substitute. First of all, we can already start simplifying r's, or we can wait not to make a mistake. Let's say it this way. R secant squared theta d theta. This r is cubed, and now I have a square root 1 plus tangent squared, 1 plus tangent squared is secant squared theta. So I have just secant squared theta inside of the square root. So that's going to be just secant squared, but still cubed, remember that. Finally, we can start simplifying. So we have r cancels out with r cubed and gives you r squared in the denominator. Secant squared theta, secant cube theta, d theta. Did you see what just happened? Let me explain. Square cancels out the square root, so it only stays as cube here. That's why there's a cube in the denominator. R cancels out with this cube and gave you r squared. Finally, the integral becomes d theta all over r squared secant squared theta. Squared or not squared? Just secant, no squared. So this whole secant squared goes away and 3 becomes 1. Whew, good. But that's integral, we still need to integrate that. Can you integrate that? How to integrate that? Remember, at the beginning they told us that a, r, and a are constants. So we can kick out 1 over r squared outside of the integral. That's already promising. Then what is secant? That's 1 over cosine, right? So it's going to be 1 over cosine theta, d theta. Dividing by a fraction means multiplying by the reciprocal, or basically flip the fraction. That's going to be integral of cosine theta, d theta. Well, do you know how to integrate cosine? Yes, you do. This is sine. So finally, actually, it was not too bad. I always say if you stuck with trigonometric functions, I mean like at the very end what we did, just write down the definitions. So what is 1 over secant? I don't know. How to integrate that? Then write down the definition of secant and maybe it will help you. So in this case, it did help you. Okay, so what did we do? That's really far from the answer, so don't relax yet. We were trying to integrate this integral, but with no limits yet. So no a and no infinity. We succeeded, but unfortunately, to succeed, we used trig substitution. We created theta as the angle, so nobody knows what theta is except us. Sine theta was introduced by us as a substitution. We need to go back to x, and you remember how we usually do. We build a right triangle to find sine theta. So this extra step, what is sine theta? Okay, usually we do it this way. We go back and check what was our substitution. The substitution was x equals r tangent theta. Let's write down. This is key information. X equals r tangent theta. Done. Now, let's write down what it means. That means that x is just r sine theta over cosine theta. Okay, so that's good. We actually need this piece. We need sine theta. We need to find sine theta in terms of x. So let's solve for sine theta. If x equals r sine theta over cosine theta, then let's divide by r and multiply by cosine theta. Make sense? Then sine theta will be x times cosine theta over r. Does this make sense? So we solved for sine in terms of x. Still, we don't like that we have cosine theta over there. And here's an interesting idea. So this is already good, but we just need to get rid of this theta now. The moment we get rid of this theta, everything will be in terms of x, and that's perfect. Let's keep having this conversation. Let's keep x and r. That's not a problem. Cosine, as we know, can be written as 1 over secant. We just had it before, 1 over secant. If secant is 1 over cosine, then cosine is 1 over secant. That makes sense. Why this is helpful? Because secant has connection with tangent. if you remember, or if you don't, I'll write down for you right now. Secant squared theta is 1 plus tangent squared theta. Or maybe you saw this formula as secant squared minus tangent squared. Well, if I want to jump from secant to tangent, I can just put square root on both sides. If I don't have secant squared, let's put a square root. So I will have x over r, 1 over, and secant becomes a square root 1 plus tangent squared theta. You will ask me, why are we doing all of this again? Because this theta, or particularly tangent theta, has connection with x, and now we're gonna finally get rid of this theta completely. So we got rid of the original, we got rid of some of this theta. Sine theta was substituted with x times stuff. But now we need to get rid of cosine theta. Cosine theta was converted into secant. Secant was converted into tangent. Tangent is x over r. So from this box, I'll put it in the box. From this box, we not only found sine theta, but we also can find tangent theta. We can solve for tangent theta. It is x over r. Then let's take this circle and plug it over here, and we are done getting rid of theta without even using any right triangles. So it's going to be x over r, 1 over a square root, 1 plus tangent squared. So 1 plus x squared over r squared, because tangent in blue, you see, is x over r. Okay, well, we can also simplify that if we want to, and we should. X over r, let's create common denominator because it doesn't look nice. So it's going to be r squared, let me change the color for you, r squared. So it's going to be r squared plus x squared inside of the square root. But r squared is can be kicked out from the square root, but we're dividing by it, as you can see. So that is going to be, we're dividing by this purple fraction. That means we can multiply by the reciprocal. So it's going to be square root of r squared at the top and a square root of r squared plus x squared at the bottom. Almost done, almost done. Now look at this magic. R squared square root is just r. R cancels out with r. So we get a final answer. After all this madness, the answer is x all over a square root r squared plus x squared. And that is finally, what are we doing here? We're trying to solve for sine. And sine was not even isolating standing over there. Sine is actually multiplied by 1 over r squared. So don't forget about that. So why are we doing that? That was the result of the integral. So the result of the integral, thus, I like this word, thus, the integral which we had from the first time, dx, r squared plus x squared raised to the 3/2 with no borders yet, is 1 over r squared, this is what I'm looking at, 1 over r squared sine theta, but sine theta is this. So it's x over the square root r squared plus x squared plus c. Okay, so that's indefinite integral. And now, last step, u equals, you can ask me like, what the heck, you're talking about which u? U was over here at the very beginning. U is actually this integral we just wrote, but from a to infinity, and don't forget to multiply by a and r outside of the integral. Okay. U is, there was a and r. That was originally in the formula there. Now I'm plugging this thing where? It's not like I'm plugging, I'm gonna copy it And now, instead of plus c, do you know what I'm going to do? I'm going to put a bar and calculate this from a to infinity, which is a bad notation, of course. As you remember, we're not supposed to plug infinities. We're actually supposed to use limits. So let's do it. But before we do it, we can simplify this r and r in the denominator. So I'm having a over r. Then I have a limit. Then I have x all over r squared plus x squared. A bar from a, what do you want, b or t? Let's do b. b, let's put it in green. b goes to infinity. Plug the top minus the bottom. We know how to do that. a over r. Limit. b goes to infinity. Where do I plug in? Into x or into r? Do you know how to find out? You need to go back to the integral and see the variable for the integration. So integral is in terms of x because of this dx. Then those limits of integration are also in terms of x. That's how I know I'm plugging into x, not into r. Well, also I was told that r is a constant, but in the future you will have many variables into multivariable calculus. So you need to pay attention on that. So I'm plugging into x. Then it's going to be b, a square root, r squared plus b squared, minus a square root, a squared, no, r squared plus a squared. Let's put brackets. Now, what's the difference between a and b? A is a constant. B is a moving variable in my limit. Here it is. So b actually explodes to infinity. If this first part explodes to infinity, everything explodes to infinity. If not, then we're fine. So let's see. This takes you to calculus 1 material when we looking at the limits of this type b all over r squared plus b squared when b goes to infinity. How to find those limits? Remember, you're supposed to divide by the highest power, by the denominator with the highest exponent. Usually the way I explained, find the leader of the top, that's b. At infinities, you can do a shortcut like this. Find the leader of the bottom, that's b squared, but it's inside of the square root. There's going to be a square root of b squared. You can ignore this r squared because it's just a constant and it doesn't influence what's going to happen with infinity. Well, b over b squared inside of the square root is just 1. So that means the speed of the numerator here was the same as the speed of the denominator here at infinity. This only works at infinity. Those are called limits at infinity. Since the speeds were the same, the whole thing was going to 1. So the answer of this amazingly long problem, and good job if you're still watching this video, that means you have very good attention span. So that's u. u is a over r, brackets, 1 minus a all over the square root r squared plus a squared. Oh my gosh, we did it. It's amazing. Let's put it in the rainbow box and be proud. How many techniques did we use? 3 or even 4. First, we figure out how to do improper integral. No, improper integral was later. We first figure out that we need to plug in tangent. We finished it. Then we will figure out how to now convert sine into x. And we avoided actually using a right triangle. This was this step. We avoided using right triangle. We used lots of different ideas. Definition of tangent, sine over cosine, solved for sine. Then cosine was 1 over secant. Then we used this identity. So we used lots of stuff only in this step. Finally, when we finished it, we found the answer for indefinite integral. Then we figured out that the definite integral actually is improper integral because of the infinity. So we had to use limits. Then for the limit, we had to go back to the limit topic and figure out what happens with the limits at infinity. We figured out that it gives you 1. So the answer was actually finite number. Can you imagine if after all of this, the answer would be infinite number? That would be upsetting because then everything just diverges. But now you know that this has connection with the electromagnetic theory. Magnetic potential, U, is actually a formula that involves improper integrals. Thank you for watching. See you next time.